As I noted last week when we met, we're not going to cover section 9.2, which is all the shapes of the polar graphs. That's cardioids and limacons that I showed you. Instead, we're going to move to section 9.3, which is the complex plane. A complex number z, x equals y plus x plus yi, can be interpreted geometrically as the point xy. So we're used to calling a complex number a plus bi. This is the same thing, only using the letters x and y. We talk about the complex plane. The complex plane puts the real axis on the x-axis and the imaginary axis on the y-axis, which means that if we have a complex number, x plus yi, we would go over x and up y to get to that point on the plane. Its real part is x, its imaginary part is y. If we have a point that's on the real axis, for example, a point here, this point would have an x-coordinate, but its y-coordinate would be 0. That point would be a real number plus 0i, just a real number. If we had a point on the y-axis, the imaginary axis, that point would have an x-coordinate of 0 and a y-coordinate of some number. So it would be 0 plus yi, or just y times I. That's an imaginary number, a pure imaginary. So points on the x-axis are real numbers, and points on the y-axis are pure imaginary. Anything in any of the other quadrants is a non-real complex number that has both a real and imaginary part. When we talk about complex numbers, we talk about the modulus or magnitude of the complex number z. The modulus or magnitude, I think I'm going to use the word magnitude more than modulus. The magnitude is denoted by what looks like absolute value bars, and we're going to see why that is in a second. The definition of the magnitude is the distance from the origin to the point z. The distance from the origin to point z, and again, point z, if it's a complex number, is written as x comma y, where x is the real part and y is the imaginary part. So if we look at this picture, I want to find the distance from the origin to this point, x comma y. It's the point x comma y. So I go across x and up y to get there. If I want to find this distance, the magnitude, the straight line distance, I could use Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. And if I want to solve that for the magnitude, I would take the square root of both sides. So the equation that we use to find the magnitude is the square root of x squared plus y squared. Now, we saw that the notation is the same as absolute value, and sometimes that magnitude is called the absolute value of z. You remember the definition of absolute value for real numbers is distance from 0. That is the same thing for any number on the real axis. This point on the real axis is the square root of x squared away from 0. So absolute value is actually a special case of this magnitude formula. What we're going to do is we're going to take these complex numbers, x plus yi, and we're going to write them in both rectangular or Cartesian form, x plus yi, and in polar form, when we talked all about polar numbers in section 9.1. So in polar form, the complex number x plus yi is written as r cosine theta plus r sine theta times I. If you remember, when we were converting polars and rectangulars, we said that the x-coordinate is always r cosine theta, and the y-coordinate is r sine theta. And we see those show up in this formula. Now, this is the form that we're going to write our final answers in. All that is the r factored out in front. When we write these, the r is going to be greater than or equal to 0, a positive radius, and the angle is between 0 and 2 pi. The angle theta is called the argument of z. We can see that in this picture. And the radius is the magnitude of z. Oops. We said in the last picture that the magnitude is the length of this hypotenuse. That's now the radius of the polar form. So the calculations you do today are going to fit very closely with what you were doing in section 9.1. Here are some examples. We're going to plot a point in the complex plane and then write the complex number in polar form. So these are all going to be points that come off of our special angles again. So we should see our 30, 60, 90s and 45, 45, 90s in this section tonight. I'm going to plot the point z equals square root of 3 minus I. If I have square root of 3 minus I, that's minus 1I. So this is the point where the x coordinate is square root of 3 and the y coordinate is negative 1 because this is x plus yi. So I'm going to plot the point where x is square root of 3 and y is negative 1. I go over square root of 3 and I go down 1. In order to put this in polar form, I need to get it into the form r cosine theta plus I sine theta. I need to find the radius, which is this hypotenuse, and then I need to find the angle theta, which goes around this way. This triangle is our normal 30, 60, 90 with a shorter leg of 1. So shorter leg times square root of 3 gives me longer leg. Shorter leg times 2 gives me the hypotenuse. My r is 2. Then, and you can also use Pythagorean theorem to get that. And then I want to find theta, this angle all the way around. The angle in the triangle is 30 degrees or pi over 6 radians. So if this angle in here is pi over 6, I am 1 pi over 6 short of 2 pi. 2 pi is 12 pi over 6. Take away 1 pi over 6, and my angle is 11 pi over 6. That's my theta. So when I write this in polar form, I put the r first, so my answer is 2 times, and then I write cosine of 11 pi over 6 plus I sine 11 pi over 6. That's my final answer. Here's another example going in that direction. I have the point 5 plus 5i. So my x is 5 and my y is 5. When I plot this point, it's in first quadrant, and I go over 5 and up 5. My radius is the hypotenuse. This is a 45, 45, 90 triangle. So the hypotenuse is leg times square root of 2. My angle goes from 0 around to 2 pi. This is in first quadrant, an angle of 45 degrees or pi over 4 radians. So I'm going to plug into the formula. R, and then parentheses, cosine theta plus I sine theta. We can also go in the opposite direction and plot the point when we're given polar form and change it to rectangular form. In this example, we're given the polar form of the number, which is 2 cosine theta plus I sine theta, cosine 30 plus I sine 30. So from this formula, we know that the r is 2, this number here, and that the theta is 30 degrees. So I'm going to draw a 30-degree angle with a radius of 2. And if I draw this right reference triangle here to get the x and y coordinates, that's my 30-degree angle. It's my 30, 60, 90 triangle. Take the hypotenuse, divide hypotenuse by 2 to get the shorter leg, multiply shorter leg times square root of 3 to get longer leg. So my x coordinate, I'm going to the right square root of 3, so that's positive square root of 3. And my y, I'm going up 1, so that's positive 1. My answer is square root of 3 plus 1i. One more example. I'm given 4 times cosine 3 pi over 4 plus I sine 3 pi over 4. 4 is my radius. 3 pi over 4 is my theta. So I'm going to draw 3 pi over 4, which is in the second quadrant with a radius of 4. I'm going to make my reference triangle down to the x-axis in a 45, 45, 90, since this is over 4. The leg times square root of 2 equals hypotenuse. So take the hypotenuse and divide by square root of 2. That gives you 2 times the square root of 2 when you rationalize. Each of these legs are 2 root 2. Before you do anything else, check your signs. I'm in the second quadrant, so the x-coordinate is negative and the y-coordinate is positive. When I write this in x plus yi form, my x is negative 2 root 2 plus my y is 2 root 2 times I. And that's the rectangular form of this complex number. You're going to do just a couple problems today. Tomorrow there will be brief notes and more problems to do. Make sure that you are using those 30, 60, 90, and 45, 45, 90 ratios to get exact values for these. We don't want to just throw things in a calculator and get rounded values. And then tomorrow we'll give you a little more reason for why we would do this.